Hello everyone, and thanks for joining us on today's webinar on how to design an efficient and reliable CubeSat system. My name is Amin. I'm an RF application engineer at EMWorks. So before we start, I would like to give you a short summary about what we are going to discuss today. So first, we'll talk briefly about CubeSats as well as some of its benefits. After that, we'll look at some of the antenna design challenges. At the end, we'll have a live demo. So in case you have any questions, I'll be happy to answer them at the end of the presentation. So before we go ahead, I would like to give you a short introduction about our company, EMWorks. EMWorks is an electromagnetic simulation software company based in Montreal, Canada. We cover both low and high frequency applications. Our products are embedded in the most popular CAD platforms, namely SolidWorks and Inventor. They cover a very wide range of applications, ranging from electric motors, transformers, and power electronics, to antennas and various wireless circuits and components. If you are interested in learning more about our products, you can visit our website at www.emworks.com. Alright. Now let's talk briefly about CubeSats. So what are they? So as you can see, CubeSats are simply square-shaped miniature satellites emerged in the early 2000s, reshaping the landscape of space exploration. With the smallest dimension of 10 cm by 10 cm by 10 cm, or in other words, 1U, and a mass of 1.3 kilograms, these satellites have become important in aerospace endeavors. According to nanosat.eu, almost 2,213 CubeSats have been launched to date. They are available in different sizes ranging from 1U to 12U. CubeSats offer flexibility for diverse missions, making them essential for scientific research, educational initiatives, and technological achievements in space. Next, we look at the essential elements that form the CubeSat. While these small satellites consist of various components, our focus will be on the main ones. Firstly, we have the power system. Solar panels capture the sun's energy, and the batteries store this power, providing continuous and sustainable energy source for the CubeSat. Next is the communication system. It consists of antennas and transceivers, which enables data exchange between the CubeSat and the ground stations, facilitating real-time communication. Onboard computers is another critical component of the CubeSat. It serves as the central processing unit. It ensures precision and efficiency, guiding the CubeSat through its mission objectives. Sensors and instruments represent additional vital elements of the CubeSat. They collect crucial data, enabling scientific research and providing valuable insight into the mysteries of space. Finally, let's look at the thermal control. Through insulation and heaters, the CubeSat is shielded from extreme temperature variations, ensuring optimum functionality in the challenging space environment. Now that we have explored the key components of the CubeSat, let's look at some areas where CubeSats are being used. CubeSats have revolutionized space exploration across diverse missions. In Earth observations, CubeSats like Planet Labs' Dove satellite capture high-resolution imagery, monitoring Earth's surface, weather patterns, and environmental changes. In scientific research, CubeSats like Marco, or in other words, Wall-E and Eva, have made significant contributions supporting NASA's InSight mission to Mars and demonstrating their capability in space exploration. CubeSats also play a big role in testing new technologies and providing students hands-on experience in satellite design and operation while conducting impactful space-based research. Next, let us see some of the advantages of using CubeSats. CubeSats offer many benefits for various missions. They are quick to make, taking less than 2 years to fabricate, allowing for swift response to mission needs. Additionally, they are less expensive than regular satellites because they use simple, off-the-shelf components, which reduces costs. Lastly, CubeSats are small, not only cutting expenses, but also making less space debris. Now let's dive into some challenges with CubeSat antennas. We all understand how important antennas are for CubeSats, as they ensure successful communication in space. However, these antennas encounter obstacles like size, weight, and power restrictions. Achieving high-gain antenna is crucial to ensure the signals are strong enough for good communication in space. Achieving the desired gain and radiation pattern in small-sized antennas can be difficult. Engineers must optimize the design to maximize performance within the constraints. Finally, CubeSats are being endowed with more challenging missions that require high data rates, which must be supported by high gain direction antennas. Overcoming these challenges is essential for the success of CubeSat's mission. Now we have talked about some of the antenna design challenges. Let's look at now at an example of CubeSat antenna. So as we can see, we have a printed Yagi antenna. The antenna is printed on FR4 substrate. The antenna has total dimension of 10 cm by 9.8 cm. The antenna is designed to operate in the S-band. It consists of 4 elements. So basically we have a reflector, we have the driven element, and 2 directors. So first now let us study the performance of the antenna without CubeSat. As we can see on the graph on the left, the antenna resonates at almost 2.35 GHz. At this frequency, the antenna has a return loss of almost minus 14 dB. On right, we can see an electric field animation at the resonant frequency. Now let's look at some of the antenna far field parameters. In EMWorks, we have what we call far field parameters table. So this table basically summarizes important far field antenna parameters. For instance, for this antenna, it has maximum gain of almost 3 dB and a total efficiency of 70% at resonant frequency. On the left, we can see a 3D radiation pattern of the antenna. So we can see the antenna has maximum gain, and it's this, and the maximum gain is along y-axis. And this is kind of expected for Yagi antennas. Now let us study the performance of the antenna when it's placed on CubeSat. So for this, we'll be basically studying 2 deployment angles, namely 90 degrees and 10 degrees. So first let's start with 90 degrees case. So for this case, as we can see, the antenna is perpendicular to the top surface of the CubeSat. Looking at the return loss plot on the left, we can see there is slight change in terms of the resonant frequency. And the reason for this is that at this angle, the antenna has less interaction with the CubeSat. As a result, there is slight change in its resonant frequency. Now let us see what would happen to its radiation. So as we can see, now the antenna has a maximum gain along the z-axis. Also, we can see there is an improved overall gain. So basically now the CubeSat is reflecting part of the radiation, and this helps to improve the gain of the antenna. On the left, we can see a 2D radiation pattern at phi equal to 0 degree. All right, now let's see what would happen if we try now to bring the antenna closer to the top surface of the CubeSat. So now we can see there is an angle of 10 degrees between the antenna and the top surface of the CubeSat. Looking at the return loss plot on the left, we can clearly see there is change in terms of the resonant frequency. So basically, as we bring the antenna closer to the CubeSat, now there is stronger coupling between the antenna and the CubeSat, and this results in detuning the resonant frequency of the antenna. Now let's see what would happen to the gain of the antenna. As we can see, again we have a maximum gain along z-axis. Also we have an improved gain of almost 80 dB. On the left, we can see a 2D radiation pattern of the antenna at phi equal to 0 degree. Alright, so now let's see what would happen if we try to change other antenna parameters. So for this, we wanted to study the effect of changing spacing d between the directors of the antenna. So through parameterization or parametric study, we tried to see the effect of setting different values of d on the return loss of the antenna. So for this, we can see by changing the spacing of the antenna, this results in changing its resonant frequency. So now, as we can see, there are a number of parameters that we can play with in order to achieve the desired performance of the antenna. Here comes the end of the presentation. Now we'll have a live demo where we'll show you how to design and simulate such antennas using EMWorks. Welcome again in this live demo. So as you can see, EMWorks is fully embedded inside SolidWorks. So basically you don't need to import any CAD geometry. Once you finish creating your structure inside SolidWorks, you can just go ahead and start your EM simulation using EMWorks. So as you can see, it's just simply a tab. In EMWorks, we have 4 types of studies. We have antennas, S-parameter, TDR, and resonance. But today we'll focus on antennas. Like any other electromagnetic simulation software, we usually have 3 main steps. First, we need to specify the frequency settings, apply material, and then assign boundary conditions. So first, let's start with the frequency settings. So once we right-click, we set properties. So in this window, we can specify, for instance, the type of accuracy, whether it's normal or high, also whether we are interested only on port solution only, or also if we are also interested in 3D field data. As for the sweep, we have different types of sweep. We have discrete, fast, single. Also we can import frequency points from a file. Also we can specify the start, the end frequency, the number of frequency, as well as the frequency step. So as for the meshing, we have 2 types of mesh. We have adaptive, and also we have the manual mesh. So for adaptive, basically the software will try to find appropriate mesh for your structure. If you are an experienced user and you know where to apply mesh control in your structure, you can also use the manual mesh. If you are also interested in studying, for instance, the temperature distribution in your structure, you can also click on thermal coupling. Next, we need to apply material. So to apply material, you simply right-click and say apply material. So you can either choose your material from our library, which comes with predefined material properties, or also you can create your own material library. Also, you can import your material library if you have one. So if you are interested in changing the material properties, you can simply right-click and set edit material. So under this table, you can change the material properties you are interested in. For instance, you can change permittivity, loss tangent, conductivity, magnetic loss tangent, thermal conductivity, and so on. So for our example, as you can see, so first let's start with the case of the antenna without CubeSat. So we have the L region, which is our radiation boundary, and also we have the antenna, which is made of FR4 material. Next, we need to assign boundary conditions. In EMWorks, we have different boundary conditions, just as port, lumped element, PEC, PMC, PEC symmetry, PMC. Also, we have radiation boundary, along with other boundary conditions. So for our example, so this is our port, so to feed the antenna. Also, we have the radiation boundary. We apply also PEC on the radiating part of the antenna. Now let's look at the mesh. So now let's show so this is the initial mesh, and this is the last adaptive mesh. Also, you can apply mesh control. So for instance, you can apply mesh controls on bodies. Also, you can apply mesh control on surfaces as well as edges. You can also specify the element size. Now we are done with the study settings. Now let's look at some of the simulation results. So first, let's start with the results table. In EMWorks, we have what we call the results table, and this table gives us summary of the circuit parameters such as generalized ACE matrix, renormalized ACE matrix, impedance matrix, admittance matrix, port result, VSWR. Also, we can see the number of conversion passes as well as the number of mesh elements. You can also export results to different formats such as text, SPC, or touchstone. Now let's look at some of the 2D plots. So this is you can see the return loss of the antenna. Also, you can see the results in tabular format. You can again export results to, for instance, text or CSV. So to generate, for example, a return loss plot, you simply right click and you choose 2D plot. So, and then you choose which study. Next, you need to specify the type of parameter, whether it's S parameter, VSW, or other parameter. So for this, we choose S parameter. We're interested in studying S11. Also, you can specify the function, whether it's dB, magnitude, angle, in degree, real, imaginary. So for this, dB. So now we can see. Now let's look at the far-field antenna parameters. In EMWorks, we have the antenna far-field parameters table, and this gives a summary of an important antenna far-field parameters, such as, for instance, maximum directivity, maximum gain, radiation efficiency, and total efficiency. You can again export results. So this is the gain of the antenna, 3 dB. So to generate this, you simply right click and you choose polar plot, and then you choose 3D polar plot. And then you choose whether it's normalized. Also, you can include the model. Also, you can see the 2D polar plot. So for instance, here you can specify whether you're interested in C and theta or phi. And then you click OK. So now you can see the 2D polar plot. Also, you can see the tabular format. Next, let's look at the electric field. So you can even animate. You simply right click, set animate versus phase. The same similarly for the magnetic field. If we right click again, set animate versus phase. Now let's study the antenna on CubeSat. So first, let's start with the case of 90 degrees. So we have our antenna and we have a coax for fitting this antenna. So we have the inner pin, we have Teflon, and this is made of PEC. As for the CubeSat body, is made of aluminum, as we can see. So for the boundary conditions, we have the port now is at the coax. We have our radiation boundary, which is the air, and also we have PEC here. Also the PEC on the outer diameter of the coax. So here shows the comparison of the performance of the antenna with and without CubeSat. So to generate such plot, you simply right click, we go to 2D plot again, and then it says 90 degrees, and also choose antenna isolated. So now you can compare the performance of the antenna. Also we can see the 3D gain of the antenna. Now let's look at the case of 10 degrees. Yeah, so we can see a shift in terms of resonant frequency. You can see the radiation pattern of the antenna. Lastly, let's look at the parametric study and how to set it in EMWorks. So as we said before, so we wanted to parameterize this distance. So for this we have different values, 12, 14, 16. So to see them, you go to parameterization, display for 12 case, and then you can display now for 14. It's moving. Also, maybe change the view. So you can see now it's moving. So for parameterization, so first you go to parameters, and then you go back to SolidWorks, and then you choose sketch. So for instance, let's say we're interested in changing this, for instance, this dimension. We click here, and the dimension is here, D3. So now we go back to SolidWorks. So create a new study, say antennas. So here we specify parameterization. Now we go to the design scenarios. Now, so we have now D3, as you can see. So we can specify the minimum value, the maximum value, as well as the step size. And here we can say generate scenarios. Yeah, that's pretty handy. So now we go back to the previous example. Let's see, for example, the S parameter versus frequency. So now say all the scenarios. So now we can clearly see the shift in terms of the resonant frequency. Here comes the end of the live demo. So to summarize, you have gained insight into the challenges associated with CubeSat antennas and the impact of varying deployment angles on detuning the resonant frequency to achieve a desired value while enhancing the antenna gain. We demonstrated you how easy and efficient is EMWorks in simulating CubeSat antennas to achieve optimal performance. With that, I would like to thank you, and now the floor is open for questions. Thanks.